Section: Introduction. In this section, we discuss the challenges faced by large language models, LLMs, in complex reasoning tasks. For instance, even advanced models like Mistral 7B only achieve 36.5% accuracy on the GSM-8K dataset, despite using techniques like chain of thought. While fine-tuning can enhance reasoning abilities, most LLMs depend on fine-tuning data created by more advanced models, such as GPT-4. The research community is exploring a complementary approach, improving reasoning without relying on superior models. One promising method is to utilize the knowledge within LLMs themselves. For example, the RAP method uses self-exploration to enhance reasoning through self-rewarded feedback. However, studies indicate that this approach faces two main issues. First, LLMs often fail to effectively explore the solution space, resulting in low-quality reasoning steps even after multiple attempts. Our experiments show that after 32 rounds of self-exploration with RAP, only 24% of the generated paths by Llama 2 to 7B on GSM-8K were correct. Second, even when high-quality reasoning steps are found, LLMs struggle to identify which steps are better or which final answers are correct, making it hard to guide the self-exploration effectively. Our findings suggest that simple reward-based guidance can yield results no better than random guesses. This problem is even more pronounced in smaller language models, SLMs, which have weaker capabilities. For example, while GPT-4 can refine its outputs effectively, similar methods may worsen performance in SLMs, hindering the use of neural language models. To tackle these challenges, we introduce self-play mutual reasoning, rStar, a new approach that enhances SLMs' reasoning capabilities during inference without fine-tuning or superior models. rStar separates reasoning into a self-play mutual generation and discrimination process. It employs a conventional Monte Carlo tree search, MCTS, for SLMs to generate reasoning steps but introduces a broader range of reasoning actions that mimic human reasoning, such as breaking down problems, proposing new questions, or rephrasing existing ones. This allows SLMs to create higher quality reasoning paths. Additionally, rStar enhances the MCTS process with a mutual consistency discrimination method. It uses a second SLM with similar capabilities to provide unsupervised feedback on the reasoning paths generated by MCTS. To improve feedback accuracy, rStar samples partial reasoning paths and asks the second SLM to complete them, considering the mutually agreed paths as higher quality. This method reflects how humans often rely on peer agreement in the absence of supervision, suggesting a higher likelihood of correctness. Our extensive experiments across 5 SLMs and various reasoning tasks demonstrate that rStar significantly improves reasoning capabilities. After just 32 rounds of MCTS inference, rStar matches or even exceeds the accuracy achieved through fine-tuning. For example, it raises GSM-8K accuracy from 12.51% to 63.91% for Llama 2 to 7B, from 36.46% to 81.88% for Mistral, and from 47.23% to 85.52% for Llama 3 to 8B. We also conduct thorough experiments to confirm rStar's superiority over state-of-the-art methods, including few-shot chain of thought, self-consistency, and various self-improvement techniques. In the following sections, we will explore related work, including prompting methods, self-improvement strategies, sampling reasoning paths, and answer verification techniques. Section Summary. In this section, we discuss the limitations of large language models, LLMs, in complex reasoning tasks and introduce our novel approach, self-play mutual reasoning, rStar, which enhances reasoning capabilities in smaller language models, SLMs, without fine-tuning or reliance on superior models. rStar employs a self-play mutual generation discrimination process to improve reasoning quality by simulating human-like reasoning actions and utilizing mutual consistency for effective feedback, resulting in significant accuracy improvements across various reasoning tasks. Section: Methodology. In this section, we outline our methodology for addressing reasoning problems using self-learning models, SLMs. We approach these problems as multi-step reasoning tasks, breaking them down into simpler subtasks. This method is more effective than traditional chain-of-thought reasoning because it allows SLMs to generate one step at a time, which is easier than producing all reasoning steps in one go. We utilize the Monte Carlo tree search (MCTS) algorithm to enhance the SLM's ability to create multi-step reasoning solutions. For any given problem and target SLM, MCTS helps us build a search tree incrementally. The root node represents the main question, while edges represent actions taken. Each child node corresponds to an intermediate reasoning step generated by the SLM. A path from the root to a leaf node forms a candidate solution trajectory. Our goal is to identify the trajectories that lead to the correct answer. We face challenges in improving SLMs. MCTS allows exploration of various potential solutions, but traditional methods yield limited improvements due to the vast solution space and the SLM's inability to generate effective solutions. Existing methods often lack diversity and struggle to generalize across tasks. While some approaches use random sampling to ensure diversity, they frequently produce low-quality solutions, leading to increased inference costs. Additionally, accurately rewarding each action is difficult without ground truth labels, making it hard to verify the correctness of intermediate steps and final answers. To tackle these challenges, we introduce our methodology, rStar, which separates reasoning into solution generation and mutual verification. We propose a richer set of human-like reasoning actions to explore diverse reasoning tasks thoroughly. We also design a reward function tailored for SLMs to evaluate intermediate steps without relying on their often unreliable self-assessments. Furthermore, we incorporate another SLM as a discriminator to verify the correctness of each trajectory alongside the generator SLM. At the heart of MCTS is the action space, which defines how we explore the tree. Most methods use a single action type, which can limit exploration. We draw inspiration from human reasoning, where individuals use various actions to solve problems. We introduce 5 distinct actions to enhance the SLM's ability to tackle complex reasoning problems. These actions include proposing one-step thoughts, generating remaining thought steps, asking and answering sub-questions, re-answering sub-questions, and rephrasing questions or sub-questions for clarity. Each of these actions contributes to a diverse action space, allowing MCTS to select actions that prompt the SLM to generate the next reasoning step based on the current state. Some actions must follow a specific order, ensuring logical progression in the reasoning process. Another crucial aspect of MCTS is the reward function, which evaluates the value of each action and guides tree expansion. We create a straightforward yet effective reward function for SLMs, avoiding self-rewarding techniques for intermediate nodes due to their limitations. Instead, we score each intermediate node based on its contribution to the final correct answer, ensuring that actions leading to correct answers receive higher rewards. To generate candidate reasoning trajectories, we start from the initial root node and perform multiple searches involving selection, expansion, simulations, and backpropagation. We use the upper confidence bounds applied to trees (UCT) method to balance exploration and exploitation during node selection. Once we reach a terminal node, we collect all trajectories from the rollout iterations as candidate solutions, which we will verify in the next section. Section Summary. In this section, we present our methodology, rStar, which decomposes reasoning into solution generation and mutual verification using a Monte Carlo tree search (MCTS) approach. We enhance the reasoning process by introducing a diverse set of human-like actions and a tailored reward function to improve the SLM's ability to explore potential solutions and accurately evaluate intermediate reasoning steps. Section: Reasoning Trajectory Selection with Mutual Consistency. In this section, we discuss our approach to selecting reasoning trajectories with mutual consistency. In traditional Monte Carlo tree search, MCTS, we usually pick one trajectory as the final solution based on a specific metric, like the one with the highest reward. However, we found it difficult to define a single reliable metric for selecting the correct trajectory. Instead, we gather all trajectories and introduce the concept of mutual reasoning consistency for answer selection. To implement this, we add a second model, which we call the discriminator, alongside our target model. This discriminator provides unsupervised feedback for each candidate trajectory. For a given trajectory, we mask some reasoning steps starting from a randomly chosen point. We then use the earlier steps as a prompt for the discriminator to complete the reasoning. This approach makes it easier for the discriminator to provide the correct answer. We check if the answer from the discriminator matches the original trajectory. If they align, we consider that trajectory valid for final selection. To illustrate our method, we can think of students solving a problem without a teacher. If one student is unsure and asks a peer to review their reasoning, and the peer arrives at the same answer, the first student gains confidence. This peer verification mirrors the mutual reasoning consistency we aim for. After applying this consistency check to all candidate trajectories, we return to our target model to select the final trajectory from those validated. We calculate each trajectory's final score by multiplying its reward with the confidence score from the rollouts. The trajectory with the highest score is chosen as the solution. We also describe our setup, which includes various models and datasets. Our method, rStar, works with different large language models, LLMs, and reasoning tasks. We evaluate 5 models across 5 reasoning tasks, including 4 mathematical tasks and 1 common sense reasoning task. In the trajectory generation phase, we enhance each target model with our MCTS, performing 32 rollouts. For most tasks, we set the depth to 5, except for one task where we set it to 8. We use a smaller model as the discriminator for efficient inference, and it processes inputs in parallel. When the target model is the smaller model, it performs self-discrimination by splitting the trajectory and using the first half as input. We compare rStar against 3 strong baseline types: single-round prompting, multi-round prompting with self-consistency, and multi-round self-improving approaches. We evaluate the effectiveness of rStar on various reasoning benchmarks and highlight 3 key observations. First, models using rStar show significant improvements in problem-solving abilities. For instance, one model improved from an accuracy of 12.51% to 63.91% on a specific task. Second, rStar consistently enhances reasoning accuracy across different tasks, while baseline methods do not perform well across all benchmarks. Lastly, even without our discriminator, our MCTS generator outperforms existing multi-round inference methods in improving reasoning accuracy. We also assess rStar on more challenging mathematical datasets, where it shows significant improvements in reasoning accuracy compared to state-of-the-art baselines. Section Summary. In this section, we propose a method for selecting reasoning trajectories using mutual consistency, where we utilize a discriminator to validate candidate trajectories by comparing answers generated from partial reasoning steps. Our approach significantly enhances the accuracy of various SLMs across multiple reasoning tasks, demonstrating that SLMs can achieve state-of-the-art performance with proper guidance in trajectory selection. Section: Ablation Study. In this section, we conduct an ablation study to assess the effectiveness of our approach under different rollout scenarios. Our method, rStar, utilizes a rollout policy for expanding the MCTS tree. While more rollouts provide additional candidate solutions, they also increase the cost of inference. We compare the accuracy of our rStar with SC and RAP across various rollout counts on the GSM-8K dataset. For SC, we gather solutions based on the number of rollouts and use majority voting to determine the final answer. We make 2 important observations. First, even with just 2 rollouts, rStar significantly enhances reasoning accuracy for SLMs, proving its effectiveness. Second, both rStar and SC improve with more rollouts, while RAP tends to plateau and even decline after 4 rollouts on Llama 3 to 8B Instruct. This decline may be due to RAP's single-type action space, which restricts effective MCTS exploration. Next, we evaluate the effectiveness of our MCTS generator against 3 baselines: the MCTS generator from RAP, SC with 128 randomly sampled solutions, and our generator that includes self-evaluation to assess the reward score for each action. We isolate the impact of answer verification methods by evaluating each generator using both majority voting and our discriminator for selecting trajectories. Our results show that our generator consistently outperforms the baseline generators across different verification methods. Additionally, we highlight that our SLM-specific reward function is effective, as self-evaluation actually reduces our generator's accuracy. We also examine the effectiveness of our discriminator through 2 experiments. In the first, we compare our approach to 2 baselines: majority voting and self-verification. We prompt the SLM to self-verify the correctness of each trajectory. Our findings indicate that our discriminator significantly enhances reasoning accuracy when verifying answers from various generators. Similar to the previous self-evaluation experiment, self-verification on SLMs proves ineffective. In the second experiment, we explore the impact of different discriminator models. We tested various LLMs, both stronger and weaker, as discriminators for Llama 3 to 8B Instruct. Our results show that the choice of discriminator model generally does not affect the effectiveness of our mutual reasoning consistency for answer verification. Notably, using the powerful GPT-4 as the discriminator only slightly improves performance, indicating that mutual reasoning consistency can effectively verify answers using SLMs.